Good morning, everyone. Okay. Good morning, everyone. It's just a few minutes after 10 o'clock, and we would like to get going. So this is understanding and detecting shear stress deposits. This is, I'm sure, be very, very interesting because it's quite different than regular varnish type deposits we get. Just reading off the bio, I'm sure you all read it, but I'll go through it quickly. Greg Livingstone is the Chief Innovation Officer for Fluitec. He has 3 decades of industrial lubrication experience, focused on how lubricants degrade and how to mitigate the risks associated with oil failure. He's developed oil analysis tests, filtration technologies, solubility enhancers, and other technologies used to increase the life and performance of industrial lubricants. He has volunteered in multiple industrial organizations, such as STLE, ICML, and ASTM. Along his journey, he's published almost 100 papers on these subjects and has helped hundreds of clients in over 50 countries. He has recently published a book called The Turbo Machinery Cholesterol, The Story of Varnish. And just as a little insight into some of the presentations that you can click on and look for free or papers that he's done, Machinery Lubrication has a number of articles by Greg, which are very interesting, covering some of these different attributes. Greg is also born in Canada, in Victoria, which I thought I'd just mention that to throw it in. So welcome, Greg, and away we go.
All right, wonderful. Well, pleasure to be here, and thanks so much for the introduction. Great, so what I'm going to talk today about is this phenomenon known as shear stress deposits. So the first thing I'll do, though, is just give a quick overview of deposit formation. This is actually a pretty well-studied body of knowledge now, and I'm sure will be a review for most of you. So I'll do a quick review of deposit formation, talk about and introduce the concept of shear stress deposits, then talk about detection, and finally mitigation. So to kick things off, just a high-level review on deposit formation. There are many different ways that an oil can degrade. And let me also just preface this by saying today I'm just going to be focused on turbo machinery applications, basically turbines, compressors. Shearing, of course, is a widely studied subject in various other aspects of lubrication, but I am just focused today on turbo machinery applications. And in these applications, we see, that one of the dominant forms of oil degradation is oxidation. We have high temperature events, such as spark discharge, microdieseling hotspots, or what we're going to talk about today, shear stress deposits. There's all sorts of interactions with external contaminants that can accelerate degradation. And we also have a whole list of other potential forms of oil degradation, additive dropout, incompatibility being a couple of them. So just a high-level review of the oxidation process. Essentially, we have a reaction with oxygen that's resulting in the loss or the addition of an electron that creates a free radical. And this is catalyzed by either by heat, by wear metals, some types of wear metals. Water can be a catalyst and further oxidation. We refer, of course, to this as the initiation phase. And then we further go on to take this little free radical and react it, hopefully with antioxidants. But this also, this radical can go on and form other species as well until we get to the termination phase. And then we see these oil degradation products polymerizing and essentially at some point agglomerating and becoming higher molecular weight species that can come out of solution of the oil. Finally, we see the impact of the oil, both physically with a formation of sludge and varnish, or in some cases, viscosity increase, and we see chemical changes in the oil, such as acid production. So I think you're all familiar with oxidation and this process. How varnish typically forms is we have some form of degradation process that creates polar byproducts that essentially these will eventually come out of solution, form deposits on machine internals, and then cause some reliability problems. So, so again, this is a high-level review. But if we, one thing that many people are not aware of is that in the world of turbine oils, most of these oil degradation products are soluble. So we'll see if this video actually plays here. But this is a this is a video showing an oil sample, badly degraded oil sample on a heater stir plate. The whole video's been sped up, and as you can see, you'll see the temperature start to increase here. And at about 40 degrees C, you'll see all of these things will start to go in solution. So it does suggest that kind of the melting point, or the point where these products transition in solution, is around 40 degrees. And how many systems are operating at 40 degrees? You may have the occasional power plant or a hydroelectric plant, but the vast majority of turbo machinery is operating at 50, 60, 70 degrees. So basically all of these products are in solution, which is why normal filters can't filter out these degradation products. It's also why when we take a test and we want to determine the varnish potential of the fluid, we have to let that test sit and age for 72 hours to allow these things to come out of solution to properly measure them. So again, that's oil degradation products are soluble. And so how do we typically go about testing this? Well, actually, there wasn't really a standardized way of testing this until 2012, when ASTM it came out with the MPC test, the 7843. But just one picture here, the typically when these oil degradation products will precipitate out of solution, this is a nice example in a large frame gas turbine reservoir. You'll see what we call bathtub rings, where the oil typically resides below where the oil is actually operating, and you have a nice warm oil. You don't actually have deposits here, but above this, where the oil is either splashing up or you have oil mist, it is hits a wall, cools down, and then these degradation products will precipitate out, come out of solution. And again, the best standardized way of going through and kind of measuring the potential of an oil to form deposits is referred to as a membrane patch calorimetry test. There's other tests as well. The ultracentrifuge is a great test. So there's other testing methodologies as well. But just one comment here on the MPC test that I want to make is that typically you would expect, as you age an oil, you'll see a progressively increasing MPC value. And so these are some results from an accelerated aging test we do. It's called the turbine oil performance prediction test. And we're basically heating the oil up to 120 degrees with some catalyst and air bubbling through it. And every 3 weeks, we pull a sample and assess the condition of the turbine oil. And as you would expect, you see the MPC increasing up to week 9, but actually interesting in this case, the MPC actually drops at week 12. So we actually, if you inspect the glassware at the end of this test, you'll actually see significantly more deposits here on the week 12, as you'd expect, the week 12 glassware, even though the MPC is lower. So it's suggesting that maybe some of these oil degradation products that are settling out here on the patch, you stress the oil a little bit more, and actually they come out of the oil and actually form deposits here on the glassware. So the moral of this story, of this slide, is that basically a 66 is not necessarily worse than a 36. If you have you're running an MPC test and you have a result that is basically anything over a 30 would be considered critical and would justify some action. But 57 is not necessarily better than 36. So basically, because in some formulations, we do see this phenomena happen. So a little bit here about the MPC test. But getting back to the deposition process, basically, we've talked about how temperatures, if you lower the temperature of the oil, it can impact the solubility of the fluid, and then these agglomerated degradation products can precipitate out in this extremely exaggerated AI-generated sample bottle here. Hopefully, this is never a turbine oil that you've seen. So solubility is one phenomenon, and another is pressure. And so pressure is why we see deposits on journal bearings. So journal bearings or thrust bearings are among the hottest spot in the system. So clearly, these deposits are not forming because these degradation products are precipitating out here on these bearing surfaces. And I have many pictures here of bearings. But typically, there's 2 points that I want to show you. Is that it is very common to see wear associated with deposits. That's a very common phenomena. And here you can see wear in virtually all of these pictures. You can see some evidence of wear that is correlated to deposits. And the second thing is that the deposits are happening in the minimum oil film thickness region. So they're happening in the hottest spot in the bearing surface. And also we see these in thrust bearings, of course, as well. The challenge with bearings. So if you have deposits in like the first picture I showed in your reservoir, most people are not so stressed about that. That's a wonderful place for deposits to form, and there's not really any impact that you have on the actual operation of the turbo machinery. It is a good clue that something is going on in the oil, and during an inspection, if you see deposits in the internals of your reservoir, it probably justifies or signifies that you should take some kind of action or investigate a little bit further. Try to get a sample of that deposit and send that off for testing. You can always learn a lot from that. But when you get deposits on bearings, now you have some pretty significant issues. The first thing is varnish acts as an insulator. So it's essentially a polymer, and polymers have many times more conductive or less conductive capacity as oil. So one of the functions of an oil is to cool the bearing. And if you put an insulator layer on the bearing surface, obviously the oil is not going to be able to do one of its most important jobs of cooling. So that's one issue. And the other is that now that we have an insulating layer and the oil's not doing its job of cooling, we see temperature excursions, and now we see high bearing temperatures, which is can be a significant cause for concern. Another thing that we have noticed that's quite interesting. When you see a temperature spike, and typically if you'll see temperature spikes on bearings that have varnish deposits on them, often we'll actually see a shift in the rotor position as well. So this is a timestamp of a bearing temperature spike event. And we also see this kind of correlating shift in rotor position. And we've seen this in many cases. And essentially, I think what we're seeing here is if we can imagine our oil film, as this varnish layer increases, it actually can push the whole rotor up very slightly. So the rotor actually can move, and then the bearing temperature correspondingly goes up. And then as that, at some point, you're not going to be able to create unlimited levels of varnish. At some point, you're just not going to be able to overcome the shaft will, the film strength of the deposit will not overcome the force required to move the shaft, and that results typically in a wipe of the deposit, and the temperature drops again, the rotor position comes down again, and often this is the point where we start to see some potential wear happening in the bearing as well. So that's one of the impacts that we see on bearing surfaces, and I think one of the phenomena, one of the signatures that we can see from a temperature perspective is this sawtooth pattern in bearing temperatures. And typically you'll see this sawtooth pattern both increase in the amplitude here, but also the average temperature will start to increase. So this is a case of varnish on a journal bearing, and this is kind of a this is a radial bearing over a 500-day trend, and you can see progressively more extreme temperature spikes to the point where you can actually have it can threaten operation. So what temperature will threaten operation? Well, typically, if we have temperatures of about 110 degrees C on a bearing, in most cases, you'll have alarms that are starting to be tripped at that point. And then unit trip are typically set at about 120 degrees C, and 132 is the region that we start to see Babbitt creep. So we clearly don't want bearings to ever get up to this level. And a lot of machines are set that if you start reaching levels of 110 to 120 degrees, you have to take some action. It may be shutting the machine down, which in some processes that just cannot be done. So you have to take some kind of action while you're operating to try to mitigate this temperature and allow you to keep operating. All right, so that's high level overview of varnish. Most of you, I'm sure, are familiar with this. Now we're going to talk about shear stress and some of the impacts that shear stress can have. So let me start this off with a case study. So this is a case study that in a small compressor, there's 3 different stages in the compressor, and just take a look at the speed of this compressor. In the first stage, 37,000 RPM, 52,000 RPM, the second and third stage. This system is moving. So they had vibration and temperature excursions in this system. So additional oil analysis were performed. What you can see along the bottom here, a graph of this sawtooth type varnish signature that we saw on a couple of the bearings. But the oil analysis indicated that everything was fine. So the oil was less than a year old. There's plenty of antioxidants left. There were no signs that it had undergone significant degradation. The MPC in this case was 5, so the MPC was low, yet the signature is suggesting that there is some type of, there could be varnish in the bearings. So this is a great example of shear stress. Shear stress is a phenomena that we see that is more common in higher speed, higher load bearing applications. And essentially what we have is molecular friction between the 2 moving parts that can generate very, very, very high temperatures in the range of several hundred degrees Celsius. And this, when you stress an oil at several hundred degrees, this leads to essentially instant oil degradation and localized deposits. And again, this is happening in the minimum oil film thickness zone. There's another phenomena that's referred to as a Morton effect. It's synchronous rotor instability and can lead to vibration. It's thought that shear stress deposits will also lead to this Morton effect that we sometimes see in bearings. And again, we see this more common in compressors than we do in turbines. And one of the reasons is that these compressors can be operating at much higher temperatures. So of course, power turbines in North America are typically operated at 3,600 RPM, in Europe and APAC, typically at 3,000 RPM. And again, this is an example of a multi-stage air and nitrous oxide compressor and a process gas expander and a steam turbine in one compressor train here. So this is a typical application that we'll see shear stress deposits occur in. From one other piece of evidence that we've seen is that here we have a picture of a varnish on a thrust pad, and we can see the hottest temperature zone right here. We actually extracted levels of deposits here at various parts of this this pad and did some analysis on it, and we identified that actually the vast majority of this was what you would typically see as organic degradation products, typical oxidatively derived varnish. However, these deposits were a little bit unique. These deposits in the middle, where the blackest level of deposit is, where the highest temperature is actually contained, it was phosphorus rich. And this was an EP-based turbine oil, so there was phosphorus in the turbine oil. Typically, you don't have EP additives reacting or activating until you have temperatures, say, in excess of a couple hundred degrees. So it's interesting here. It's suggesting that this temperature zone was hot enough to actually activate EP additive, and we actually saw evidence of that here in the deposits with phosphorus-rich deposits. So we are talking about fairly high temperatures. Just to get into this in a little more detail. The two big factors that will impact shear stress deposits are load and rotational speed. And the higher the speed, the higher the load, the higher chance that shear stress will happen here in the minimum oil film thickness. And a lot of plants will see deposits here on their bearings. So one of their first if you're in the oil industry, you'll know that if there's ever any mechanical issue in your system, it's the oil's fault. Oil is often blamed for pretty much everything. So in this case, many plants have seen deposits here on bearing surfaces, and they're like, well, I'm going to switch to a upgrade to a full synthetic PAO-based turbine oil. We have not seen any evidence or any improvement in moving from, say, a Group 2 to a Group 4 formulation. So we don't think this is as related to the formulation as it is to just a mechanical condition of the system. So if we look at this under a little more of a microscope here, we can see we have the oil layer, the deposit layer, and we have essentially, as this bearing is spinning, the oil film, it could be a 30 micron layer, the film of oil. Essentially, these molecules are essentially being ripped apart, and this is causing internal friction. And we know now that these temperatures can be very hot, and essentially this is causing localized deposit formation and the formation of these polar degradation products that basically instantly form here on the fluid. Occasionally, we'll see actually a mechanical event that could actually kind of kickstart this whole thing. So one thing that you may want to do if you have these temperature spikes is kind of look back in your history and see if you can identify some type of mechanical event that's happened. And in this particular case, this was after an overhaul. There was a cooler that was valved out after startup, and it resulted in a little peak right here, a little bearing temperature excursion. And then we actually saw now where the oil was under enough physical mechanical conditions for shear stress deposits to occur, and we saw this kind of typical sawtooth pattern happening in the temperatures. So take a look for kind of an event that could start this out. All right, so how do we go about detecting shear stress deposits? The most common thing that people think about is, well, if this is a varnish happening on my system, I should be running an MPC test. And again, we saw in the first example, MPC test is not always a reliable way of measuring this phenomenon of shear stress deposits, essentially because we have very localized deposits happening, but the rest of the oil may not be significantly degraded. So by the time you pull an oil sample, that's a long ways typically from what's happening in the bearing. The bulk oil hasn't experienced significant degradation. So you could have actually fairly new oil, 3 months old. You could have signs of shear stress deposits, these bearing temperature excursions, especially if there was an event that happened during the outage, and the rest of the oil's in perfect shape. So because MPC and ultracentrifuge and most other oil analysis tests that we're aware of are not really a reliable way, we are looking at more mechanical ways of detecting this. So vibration can let you know if shear stress deposits are happening. Temperature excursions, if you have bearing temperature probes that are continually telling you the temperature of the bearings, look for those trends. And if you see temperature excursions, then that could be a sign of shear stress deposits. And also during any overhaul, it's super valuable to visually inspect all your components, all your oil wetted components. And often this is where we'll see signs of deposits here on the bearing surface. You could see varnish happening throughout the rest of the system as well. But if we start to see high levels of deposits in the bearings that are correlated with maybe some bearing wear, you should investigate maybe shear stress deposits a little more carefully. All right. Well, what are some potential solutions here for shear stress deposits? The majority of the time, this is due to a mechanical issue. So the ideal situation is to provide a permanent fix to this, and this is done in many cases by some kind of mechanical change to the system. One common way is reducing load. However, as you can imagine, if you're operating compressors, the last thing you want to do if you're operating is to be able to reduce the load because the load is it can be directly correlated to your production. So this is really in extreme cases, and to prevent an outage, we have seen in some cases plants may lower their load by 20% or 30%. Unfortunately impacting production, but it prevents you from actually having to take the whole bearing offline or shutting your entire compressor train down. So worst case scenario, you can do that. During outages, there are some different things you can do as well. Opening up your bearing clearances is a possibility so that oil film is a little bit thicker. So offset pivot is another thing that you can do, typically towards the hottest spot in the bearing. So if you're able to tilt the bearing, that can allow for greater oil flow. And sometimes we'll see a drop as high as a 20 °F drop in temperature. Directional lubricating. This is another form of lubricating the bearings. There's a great article if you're interested in this. Heinz Block wrote a great article in this in Machinery Lubrication. It talks about directional lubrication. You can see a nice drop in temperature here as well. And also we're seeing bearings, instead of being babbited, different types of materials as well that in some cases can also reduce bearing temperatures. So those are some mechanical solutions, and these are all things that are typically investigated with the OEM, changing kind of any of the operating conditions of the system. The OEM's often involved, but unfortunately, except for reducing load, these are things that have to basically take place during an outage. So if you are operating and you don't have another outage plan for 24 months, and you cannot bring this piece of equipment down, you need to also investigate if there are any solutions that can be applied while the actual system is operating. So there is one chemical solution that we have that we've come up with for shear stress deposits, and again, upgrading your turbine oil doesn't necessarily impact, or we haven't actually seen that impacting shear stress deposits. So moving to a different type of turbine oil may not be a solution, but we have developed a solubility enhancer. It was designed essentially for long-term deposit control in turbine oils. So you typically add this at 3 to 5% in turbine oil, and it doesn't adversely impact the oil's properties or the rate of degradation, and it provides a long-term protection for the oil to not form varnish and deposits. We did not design this chemistry for shear stress deposits, but we found that by increasing the solubility of the oil, it actually is preventing, under these extreme mechanical conditions, deposits from forming. So we have seen it be successful at lowering bearing temperatures related to shear stress deposits. I just always we always just keep in mind that this is a chemical solution to a mechanical problem, and ultimately the best case scenario is to see if you can come up with an actual root cause fix to the problem, looking at some kind of mechanical fix. But this is one solution that you could look at for trying to not only maintain low varnish potential in the oil, but also to mitigate, to have online mitigation of shear stress deposits. So I'll share one case study here and where we've been able to use this technology. This was in a crack gas compressor in a refinery. This was a steam-driven compressor train, and it was used in a recycled gas compressor train that had very, very high temperatures. So the first thing, of course, is that we looked at the MPC. We looked at all of the other conditions of the fluid. The antioxidants were healthy. The oil had a strong oxidative stability. However, and even the MPC was not super alarmingly high. It was kind of a moderate level, but it wasn't suggesting that there were heavy deposits on the bearings. So this was also a scenario that we observed this rotor shaft position change, and this was correlated as well to these temperature spikes. So we added the solubility enhancer to the in-service turbine oil, and we did in fact see a nice drop in the MPC value. So it did. We would expect this to happen. We saw it, in a very short period of time. The MPC value dropped, and a year and a half later, it also was maintained low. But quite honestly, the customer, and if you're operating large compressor trains, this is actually a refinery, and you would think they would be super interested in, the MPC value or the condition of the oil. No, they didn't. They didn't care about the condition of the oil. They only cared really about these temperature excursions that were creating these conditions that were threatening a shutdown prior to their outage. And so this was really the big indicator. We saw within hours of adding the solubility enhancer to the in-service oil, basically the temperature flatlined, and we no longer saw any kind of temperature excursions. So this was kind of a 2-year trend of adding this chemistry. So this is a good example of where this where a chemistry solution was possible here to kind of overcome this mechanical issue. And again, the ultimate solution is to really look at during, if you're having these shear stress deposits, is there anything mechanically that can be done to the system during an outage to ultimately, provide a root cause solution to this? So the summary of this case study is that the refinery did not have to bring this unit down. They were able to maintain production, and they did find as well that that decon had, or the solubility enhancer had excellent deposit control properties. So the oil basically maintained a very, very low MPC value. The other properties were all fine, but the biggest thing is that the bearing temperatures spike stopped, and the rotor repositioning stopped as well. So that is just to that's my conclusion. And just to kind of summarize here, I think we see that the normal oxidative process that we see in turbine oils, where the fluid is undergoing oxidation. We see the formation of these degradation products or soft contaminants that are in the oil that often will polymerize, agglomerate, come out of solution, and form deposits throughout the internals of the system. And we can often measure this by running the MPC test. Shear stress deposits is a whole other phenomena that is particularly happening at high speed, high load applications, where we have essentially molecular friction causing very high temperatures, localized deposits that are not able to be measured by normal traditional oil analysis tests. And so there are mechanical solutions to this, and there are some potential chemical solutions to this as well. So that's I would say this is still an area of active research. I'm aware of we're doing some research with a leading university with in one of the rotating or turbo machinery labs that has a lot of experience in understanding this. But this particular phenomena is still there's not a ton of research papers on this, and I think there's still a lot of research being done to be able to predict at what point shear stress deposits will happen. So that modeling, I think, is still not done. So this is kind of an exciting area that we do seem to see some potential areas for continued learning and growth. So thank you so much for your time. And if I think I saw a couple questions come in here, flash up on my screen while we were talking. So we have plenty of time for questions that we can get into as well.
Well, no problem, Greg. Can you see the questions yourself? Or do you want me?
I cannot, but here, what I can do is actually stop sharing my screen, and I should actually be able to see the chat.
If not, I can read them out for you, whatever you want.
Okay. Oh, great. We have some great questions. Okay, so let's start off. Ken, you have the first question here. Can patch weight be a better indicator for issues than the MPC value? Yeah, Ken, this is a great question. Often you'll see a lab running an MPC test and they'll report actually the color of the patch. Basically, the MPC test is measuring the total amount of color bodies on the patch, which sometimes some additives actually produce darker hues when they degrade than other additives. So you'll see different types of hues, and there's not, so some turbine oil can produce much higher MPC values than others. So you think that maybe the weight of the patch could be valuable. I pretty much discount any weight of an MPC patch. The reason is that we have only 50 mils of oil that we're mixing with 50 mils of solvent, and I don't it's not enough actually to get a good representative level of weight. If you actually do a test just to measure the weight of the fluid, and you maybe run 300 or 500 mils of oil on a patch, that I think will give you a lot better idea of, and then I think patch weight can be a better also a good indicator, can maybe complement the MPC test, but this would be a different test than just measuring the weight of the MPC patch. I will say that we do measure the weight of our MPC patches when we run the test. Every once in a while, we'll run into an example or a case where instead of having you could have 5 or 10 or in some cases 100 times the weight on a patch, and that would certainly indicate an extreme amount of degradation. But in most cases, this would be kind of a different gravimetric test to do this. All right, Andrew, nice to see you, Andrew. Does shear stress deposits occur with diesters, polyol esters, and PEG-based fluids? Great question. Andrew, I think that we have really only studied this in turbo machinery applications, and in most cases, diesters, polyol esters, and PEGs are not used. So I would say it potentially could. However, this is just not something we've not identified it, but we've just not studied this. So this is a really that's a really good question, and I think another area for investigation. Marius, does shear stress deposits occur when PEG fluids are used? So could PEGs be an actual solution as well? So yeah, again, great question. PEGs are used occasionally in turbo machinery applications, and sometimes oil soluble PEGs are OSPs are used to increase the solubility of in-service turbine oils. We do know that OSPs actually don't positively impact, will not be a solution to shear stress deposits, and in some cases could actually make it worse. So I would be concerned about using an OSP in this application. However, using a water-soluble PEG, that is something that I think that certainly could be investigated. Okay, Ken, some of the root cause analysis seem to be bearing design and operation, center pivots, thrust pads need time to crown, fast starts can kill them. Yeah. Very, very good points. And again, I think that in designing a bearing lubrication system, there is some incredible research and modeling that's been done that can predict bearing temperatures that can occur over the entire face of a journal bearing, for example. So there's been some amazing research and modeling on that, but none of it takes into account varnish or shear stress deposits. So this is an area of modeling that I think needs to happen that can impact actually design of these systems. Great comment, thank you. Is there a minimum speed below which you typically wouldn't experience shear stress deposits? So typically we see, so again, because we don't have full modeling based on this yet, you could have a scenario where you have an extremely high, extremely loaded bearing that is rotating, say if at a power plant, if you had a 3,000 RPM bearing, but you had a very, very high load on that, in fact, that could theoretically cause shear stress deposits. But in practicality, in most cases, we're looking at compressors that have a minimum RPM of about 10,000. But again, that's just based on experience, not based on any kind of scientific modeling. So, but in our experience, we often start to see shear stress deposits at speeds higher than that. Does the chemical solution work in ammonia compressors with nitrous oxide ingress in the turbine oil? Well, first, if you do have NOx getting into your turbine oil, I am sorry, your turbine oil is going to degrade very, very, very quickly. So that is a fantastic catalyst to accelerate oil degradation. But yeah, we've applied this in several ammonia compressors and several compressors that have NOx ingression and some that don't have NOx ingression. But it can work really well in this particular application for sure. But I think the big thing, beyond just shear stress deposits happening in ammonia compressors, any kind of ingress of NOx in the turbine oil, it's remarkable how fast you'll see the turbine oil properties fail. So you see a small leak of NOx, and you may see the antioxidants go from 90% to 20% in over the course of 2 months or 3 months. So it's incredible how that can accelerate oil degradation. Does a bleed and feed help? So does taking some of the oil out of the system and replacing it with fresh oil help? Well, unfortunately, not for shear stress deposits, because actually, even if you put brand new oil in, the oil could be 3 months old. And in fact, that case study I showed at the very beginning with that 50,000 RPM Elliott compressor, in that particular case, the oil was 3 months 3 months old. So you could actually have new oil in the system, and the new oil, if it doesn't matter if you have new oil or used oil or even a PAO-based oil. If you throw several hundred degrees thermal stress on the fluid at a micro spot in the system, you have a risk at forming instant degradation and forming deposits. So doing a bleed and feed won't have any impact on this. That being said, many plants have tried this and have not seen an impact. But also, even doing an oil change doesn't necessarily help. It's ultimately you want to try to have a permanent solution by making a change to the mechanics of the system. What is the effect of fluid viscosity on shear stress deposits? It seems that maybe a lower viscosity might reduce the amount of internal friction. Yeah, so that is a really good question, and I think something that needs to be further investigated. You're exactly right. A lower viscosity can reduce the amount of internal friction, but a higher viscosity can actually give you a greater oil film. So I think we don't have an answer to your question, but this is exactly the area that needs to be further studied. Excellent question. I wish I had a good answer for you on that. What's the impact of RPBOT after adding solubility enhancer? There's no impact. If you want, I can just I can share a screen on that just to give you an idea.
Okay, Greg, while you're doing that, I'll just make a comment to everybody. If anybody has any other questions for Greg, they can contact with him. His email was in that notice of the meeting that you got. It's buried up there, but was it at the start of the presentation as well too, Greg, your email address?
Actually, it wasn't. So yeah,
Okay.
I'll be sure.
Well, it
Let me
was
go
there,
type that into chat.
there with the meeting notice as well too. So,
Well, so this is kind of an extreme example of what happens when you add a solubility enhancer to the oil. So this is, in this case, an accelerated aging test with new oil. We aged it for 6 weeks. You can see, as you would expect, a depletion in antioxidants. You'll see the RPVOT, 1,200 minutes down to 300 minutes. Typical for this formulation. You know, a lot of people think that demulsibility is a result of adding or of degrading the oil. But in fact, in most cases, demulsibility is not impacted by oil degradation products, nor is foaming. So you'll see this is kind of how a typical oil will degrade. If you add a solubility enhancer to this, you still see the antioxidants deplete. You still see, say, the RPVOT value from 1,200 minutes still goes down to 300 minutes. So it still has pretty much the same. The oil is still degrading. What's happening is that these degradation products are just not coming out of solution. They're staying. You know, once this degradation process, once you get to the termination phase in oxidation, this is somewhat of an inert, incredibly tiny or solubilized molecule that's in the oil. It's somewhat harmless until it actually agglomerates and comes out of solution, creating havoc in the system. And if you're able to actually keep this in solution, then you can actually, you know, you prevent these deposits from forming, and it doesn't impact, to answer your question, it doesn't impact the rate of oxidation or the impact of the RPVOT or additive content. So very good question. Thank you. Okay, let me just see if there's, did I miss any questions here?
no, I don't think so. I don't, we see the group of them there. I think that was the last one. Switching from group 1 to group 4, and I think you mentioned you didn't see any difference.
Between group 1 to group 4, which group do you suggest? Okay, so that's a very good question. So we've done this accelerated aging test on dozens of commercially available turbine oils, and there's two things that I'll say. The first is that there is, even though all of these commercially available turbine oils meet OEM specifications and are approved for use in your system, there's a huge range of performance. So we see some oils, in fact, the oil that I just showed after 6 weeks showed a very, very high MPC value, and pretty much, you know, the RPVOT was about 25% of new. So the oil after 6 weeks in an accelerated aging test was pretty much at its condemning limits. We've seen some other oil at the end of 12 weeks that has single-digit MPC values, RPVOT values that are in the 80 to 90% range. So there's a huge range of different performances with different turbine oil formulations. And typically, the worst performing oil that I've seen, actually, so there's some group 1s that are pretty bad. Some old group 1 formulations do really bad in this test. But in general, I would say the worst formulations we've seen are often group 2s, and the best formulation performance we've seen are often group 2s. So the base oil is not necessarily an immediate indication of the performance of the oil. There are some SHC or some PAO-based turbine oils that they do really, really well on this accelerated aging test. So anyway, that's it. I think a long answer, but it's a complex question. What group would we suggest? Typically group 2 or group 3, you're going to end up with a reasonably priced turbine oil that will give you long life and high performance. Okay, we have another question here from John. In the picture of the bearings that have experienced degradation, an area of the babbitt appears as an island in the SSD varnished area. Did the babbitt peel in this area because of increased temperature, or did the vibration damage the babbitt? That's a great question. So what we believe is happening actually that's causing this wear is that the oil, this oil wedge that's separating these two moving parts, this nice hydrodynamic film of the oil, we have a lot of pressure on this oil, and we have a lot of we have a really, really small oil film thickness, and we're depending on very low surface asperities to kind of maintain this nice consistent film. Now you start to add varnish on one of the layers of one of the surfaces, and this varnish can actually cause some surface asperities and can actually crack this this hydrocarbon or this hydrodynamic wedge. It can actually crack this and cause some metal-to-metal contact. So this is the phenomenon that we believe that's causing this metal-to-metal contact. But you're right. If you do have temperatures that are in the several hundred degree range, that is absolutely the range past Babbitt creeping. But actually, we're not actually measuring this at the bearing surface. All of this is happening in that microfilm of oil. So it's all happening in the oil film. There's just not a way to actually put a temperature probe in the oil and measure what the temperature is in this, in this 20 or 50 micron film of oil. But the internal this internal friction is causing very high temperature in the oil, not necessarily at the bearing surface, and that is what is causing this this shear stress deposit. Great question, John. Thank you.
Okay, so we're a few minutes past our time, but I think it was very, very good, Greg. It was great. A lot of good questions. So hopefully we'll generate some more. Do you want to put your email in the chat just so people have it, or
I sure will.
handle it, Greg?
There you go. Wonderful. Well, Ken and Toronto SQLE chapter, it was an absolute pleasure to be able to speak with you, and I really appreciate the invitation. And also just awesome questions, as I'd expect from this group, but just fantastic questions. So thank you very much.
Okay, super. Well, with that, Payman, do you want to stop the recording? And thank you very much, and have a great month till our next talk. Thank you. Bye for now.
Thank you. Bye-bye.